blood. Actually, it is made where? Where is the urea made? In the liver. Okay, so the urea is made in the liver. Then it can go safely in the blood to the kidney to be excreted in the urine. Okay? Okay, so today we're going to talk about the urea cycle. We have mentioned yesterday all the enzymes that handled the amino group. Remember, we said that to break the amino acid, we need to remove the amino group. And how do we remove the amino group? We said there are two steps. What are they? Transamination. So in transamination, we funnel the amino group to glutamate, which acts as a temporary storage of this amino group. And then glutamate can be deaminated. Okay, so it will undergo oxidative deamination. Right. You should know the transaminases, the two famous transaminases, AST and ALT. You should know their products. You should know that the reaction is reversible. And we mentioned yesterday why AST is more favorable in the direction of making aspartate. Yes? Yes, because aspartate is actually a way of getting rid of ammonia, okay, because it's going to enter the urea cycle. Okay? This urea cycle is unique in taking place in both the mitochondria and the cytoplasm. The first two reactions start in the mitochondria, and then the rest will take place in the cytoplasm. So reaction 1, which is the formation of the first product in the urea cycle. It's very small, but I will show you in the next slide in more detail. So this is reaction 1 and then reaction 2. And then the product that is formed from reaction 2 is going to go in the cytoplasm, and the reaction will continue in the cytoplasm. Clear? Okay, so when you study this at the end, now you cannot see it, but when you study this, you have to pay attention to the color. Okay, the reason I put this diagram because it has the color. It shows you how the amino group here, okay, is from aspartate will enter the urea cycle here at this stage, and is going to be incorporated at the end. And this is the other amino group, which is coming from the free ammonia, which is produced from the different amino acids. Okay, so this is the two sources of the ammonia, and you should be able to follow them in the reaction. Clear? Okay, so let's take a closer look at the urea cycle. Can you see this better in the back? Yes? No? You can't see it? Okay, you have it on the screen. You can watch it on the screen with your colleague, unless he's doing online shopping. Okay? I'm just joking, okay? So, this is the first reaction of the urea cycle. It is the most important reaction because it is regulated step, so it is deregulated step of the urea cycle. So this first reaction, we're going to combine ammonia with CO2 in the form of bicarbonate, and ATP to form something called carbamoyl phosphate. And if you want to give a name for an enzyme that will produce carbamoyl phosphate, what will be the name of this enzyme? Carbamoyl phosphate synthetase. Okay, so this is the enzyme that's going to form this molecule, which is basically, if you look here, so what is carbamoyl phosphate? It's made of a phosphate group, carbonyl group, and amino group. Okay, so this is carbamoyl phosphate, a combination of amino, carbonyl, and phosphate group that we added them all together, and it is activated, this reaction is activated by N-acetyl glutamate. Which amino acid you can recognize here? Glutamate. Okay, what did we learn about glutamate? Yeah, so all the amino acids that we want to break down, we will remove the amino group from them, and then we will give it to alpha-ketoglutarate to store it inside glutamate. So after a protein-rich meal, the level of an acetyl glutamate will go up. Because remember, those proteins are being digested into amino acids, and all these amino acids to degrade them. The first thing is to remove the amino group, and who's collecting these amino groups? Glutamate. That's why after a protein-rich meal, N-acetyl glutamate will go up and will start telling the body, activate the urea cycle. We need to get rid of this ammonia as urea. I'm hearing something. Okay, so N-acetyl glutamate is an obligate activator of this first step. We have learned in Mol 1 the definition of obligate activator. Yes. So the reaction will not happen without an N-acetyl glutamate, which is the obligate activator. بيجي باخد منك التليفون ولا بتشيله؟ Okay. I said put it away. Put it away. You have to put it away. If you see it, you are tempted to look at it again. Okay. So this is the first step that you are required to know in detail, and we will come back to it because there is a disease associated with it. There is a genetic deficiency in this enzyme. As a result, carbamoyl phosphate cannot form, and as a result, urea cannot form. And what will happen? There will be accumulation of what? Ammonia. So the patient will have hyperammonemia. We'll come back to it at the end. Okay, so this is the first step of the urea cycle. What about the second step? I think I have, yeah. So this is the first step. You can see it better here. The formation of carbamoyl phosphate, and acetyl glutamate is the obligate activator. And the enzyme is carbamoyl phosphate synthetase 1. When we say 1, it means there is a 2. Okay, do we have 2 here? No, but we will see it in the pyrimidine pathway. Okay, so carbamoyl phosphate synthetase 2 is an enzyme in the pyrimidine pathway. Okay, but you need to be able to distinguish between carbamoyl phosphate synthetase 1 and 2. Okay, so it means that there is 2 enzymes that will form carbamoyl phosphate synthase. So it means also that carbamoyl phosphate is involved in another pathway, okay, which is actually the formation of something called orotic acid. What is orotic acid? We will learn about it later, but for now you should know that if we have too much carbamoyl phosphate, it will accumulate and lead to the formation of orotic acid. Okay? Because this is important for the enzyme deficiency that we will learn about later. Okay, so this is the first step. What about the second step? Once we have carbamoyl phosphate, it's going to combine to ornithine. What is ornithine? It's an amino acid. But we don't recall learning about ornithine. It's not among the 20 amino acids that we have learned before. So it's an amino acid which is not present in proteins. Okay, because we have the 20 amino acids that we know which are in protein, but there are some other amino acids which are not part of protein. Ornithine is an example of that. Okay? So carbamoyl phosphate will react with ornithine to generate something called citrulline. Okay. What is the enzyme? It's called ornithine transcarbamylase. Why it's a transcarbamylase? Or what does transcarbamylase mean? Yes, it's going to transport the carbamyl. Yes, the carbonyl and the amino group, and it's going to add it to ornithine to generate something called citrulline. And the enzyme can be abbreviated as OTC. We'll come back to it because there is a disease called OTC deficiency. Can you hear me?
Yes.
Yes? Can you hear me?
Yes.
Okay. So, yes, there's 2 and only enzyme deficiency that we will learn about. There are others, but you are not required to know them. Okay, so once citrulline is generated, we said it's going to go to the cytoplasm, and the urea cycle will continue in the cytoplasm. Okay, so the first 2 steps take place in the mitochondria, and then the other steps will happen in the cytoplasm. Yes?
Using the matrix.
Yeah, mitochondrial matrix. It's written in the slide. Now, what about the remaining 3 steps? we need to memorize them? You should be familiar with them. Okay, you need to understand them. Okay, there are no disease associated with them, but you will see them as distractors in questions like, what is the rate limiting step of the urea cycle? So you will have carbamoyl phosphate synthase, you will have the OTC, and then I need choices for C, D, and E. So I have to use those enzymes. But you need to understand the story because you need to know how we are making urea. So how we are making urea? Citrulline will react with aspartate. So here comes the second amino group. The second amino group is donated from aspartate. So if in a test I ask you, where is this aspartate or which enzyme contribute to the amino group of aspartate? No. The amino group in aspartate is coming from where? From which enzyme? AST. Okay, it's coming from AST. It's not coming from this enzyme. This enzyme is going to combine citrulline with aspartate to form argininosuccinate, which is going to be cleaved to give me arginine and fumarate. And then arginine will be degraded by arginase to give me urea and ornithine. And ornithine will go back to the matrix of the mitochondria and the cycle continue. Because ornithine is recycled, that's why we call it a cycle. Okay, so the important part here is to know that this is the aspartate joining in the third stage or third reaction. And it's important to know that once we release or we fold urea, ornithine is going to be recycled. Clear? Good. So, what do we need to know here? We mentioned that after a high protein meal, the N-acetyl glutamate will raise, and this will activate the first step, which is the rate limiting step of the cycle. We also mentioned in star here, the two amino group are coming from the free ammonia, which is going to be incorporated into carbamoyl phosphate, and then it's going to join the second amino group, which is coming from aspartate. Okay, so you need to know the path of the amino groups. You need to know that the urea, which is made in the liver, will safely go to the blood, from the blood to the kidney to be excreted in the urine. Do we have a test to measure urea in the blood?
Yes.
Yes, we have a test called BUN. What is BUN? Yes, blood urea nitrogen. It's actually a measurement of the urea in the blood. Okay? It is used both as an indication for liver and kidney dysfunction. Why? Because urea is made in the liver, but it is excreted in the kidney. So if we have a patient with elevated BUN, yes, this means that the kidney is not being able to excrete that urea. So there is a kidney dysfunction. If you have a patient on the other side with a low BUN, it means that we are not forming urea. Okay? So it means that the liver is not working properly. Okay? So this is regarding the BUN test. Okay, the last part of this lecture is to talk about the genetic deficiencies. The most important thing is to be able to distinguish between those two deficiencies, okay? So whether it is carbamoyl phosphate synthetase 1 deficiency or whether we have ornithine transcarbamylase deficiency, it's a genetic disorder that is going to result in a problem with the urea cycle, so we cannot form urea. And as a result, what will happen? Ammonia will accumulate. So the patient will have symptoms of hyperammonemia. What are the symptoms of hyperammonemia? What are the symptoms of hyperammonemia? What's the meaning of hyperammonemia?
Hyperammonia in the blood.
Okay, so it means what? Excess ammonia in the blood. Okay, what are the symptoms in a patient? Yes?
Sleeping a lot.
Or playing with the mobile phone? Okay, so the patient will have symptoms of hyperammonemia in both cases. They will both have decreased bun. And what is bun, we said? Yes, so it's a measurement of the urea in the blood. So what will happen to bun? It will be decreased because we can't form urea. Another thing that will be increased in the blood is glutamine. Why glutamine will be increased in a patient with a defect in the urea cycle? We can't form urea, so what?
Accumulation.
Accumulation of what? So we will have accumulation of what?
Spotted.
Ammonia, right? Where is the ammonia coming from? From glutamate, right? So instead of donating the amino group, now glutamate is going to acquire an amino group and will form glutamine. Now, why glutamine, not all other amino acids?
No. Because it's the one that carries it in the blood.
Yes, because when we studied this at the first slide here, we said that we transport ammonia as two forms. Glutamine, which is in most of the tissues, alanine from muscles. But this is like when you have lots of pyruvate in the muscle. So the main transport form is glutamine, and this is the one that will go up in case you cannot form urea. Okay? Besides ammonia, of course. So you will have hyperammonemia and you will have increased glutamine. So the question is, if you have a patient who's showing symptoms of hyperammonemia, increased glutamine, decreased bun, and all the physiological symptoms or the physical symptoms, so he's having edema, lethargy, convulsion, coma, and death, how can you tell whether it is OTC deficiency or carbamoyl synthase deficiency? Yes, so you will check for orotic acid. If the orotic acid is high, it means that the patient is having this deficiency. If the orotic acid is low or normal, or is not present in the urine, because it should not be in the urine, it will appear in the urine if it is spilled from the blood. So a low orotic acid means that there is this deficiency. If there is orotic aciduria or accumulation of uric acid in the urine, this means that this is the deficiency. Why do you think this is the case? We have to look here. So we have two deficiencies. One is with this enzyme and the other is with this enzyme. Let's look at this enzyme. If OTC is missing, then we cannot form which product? Citrulline. So we stop at which product? Carbamoyl phosphate. So what will happen to carbamoyl phosphate? As I mentioned at the beginning of this lecture, it will accumulate and then eventually it's going to leak because it's forming where, in which structure? In the mitochondria. It will leak to the cytoplasm and it will participate in the synthesis of pyrimidine, and the first pyrimidine to be formed will be orotic acid. Okay? So because OTC is deficient, carbamoyl phosphate will leak from the mitochondria to the cytoplasm, will participate in the pyrimidine pathway, forming too much orotic acid. It's a way of the body to deal with this carbamoyl phosphate. If we don't have so if it's not the OTC, if it is only a deficiency in carbamoyl phosphate synthetase 1, yes, so we're not starting this pathway, so we just have hyperammonemia, we don't have carbamoyl phosphate accumulation. That's why there is no orotic acid urea, okay, in carbamoyl phosphate synthase deficiency. So to remember the difference, you have to remember that this is come first, and this is the formation of carbamoyl phosphate. If this is not happening, then carbamoyl phosphate is not going to leak, and there won't be any orotic acid. Clear? Okay, so this is all explained here. Okay, so you can see the difference between the two defects. And how do we treat a patient with a urea cycle defect?
Low protein.
Yes, low protein diet. Okay, so there are other genetic defects in the urea cycle. You might want to read about them in the book, but for this course, I think 2 diseases is enough for you, and that's the one that you like the most in cake, and that's why I'll stress those 2 diseases. Okay, so with this, we conclude the urea cycle. Okay, so as I said before, make sure to know that the pathway starts in the mitochondria, it continues in the cytoplasm. Make sure to know the source of the amino group and the path the amino group are following. And like I said, a common question is, we have ammonia, free ammonia, and aspartate as the donors of the amino group in the formation of urea. And if they ask you where is the carbon atom coming from, it's from CO2. Because the first step is the bicarbonate reacting with the ATP. Okay, I finished early.